All right, on to the last topic for this week. Previously, we've spent a lot of time talking about alkenes. We've not spent as much time talking about alkynes because the reality is alkenes and alkynes belong to the same functional group family. So even if we don't talk much about reactions of alkynes, you need to draw conclusions and make generalizations about what alkynes do that are similar to alkenes since they're in the same family. So we've talked about similarities between alkenes and alkynes, and every reaction we've talked about so far, basically, the reaction of alkene and alkyne would be the same. Slight differences here and there, but the reactions of the alkenes and alkynes would be the same. Today, we are starting to talk about a reaction of alkynes only because alkynes have a characteristic that alkenes do not. Terminal alkynes have a carbon that is sp that has a hydrogen connected to it. Terminal alkynes, that sp carbon has a hydrogen on it that's reasonably acidic. Alkene hydrogens are not reasonably acidic. Alkyne hydrogens are reasonably acidic. So what do we do with that knowledge? Sodium hydride, that's this first guy, sodium hydride is a base. Hydride with its 2 electrons, it's a base. That base can take electrons from that hydrogen, giving carbon a lone pair. This that I have drawn is the conjugate base of that terminal alkyne, and this is hydrogen gas, the conjugate acid of my base that I used. Okay. This sodium amide, NaNH2, that's an ionic species as well. That's an NH2 with a minus. It's a base. That base can take a hydrogen from that terminal alkyne and give electrons to that carbon, resulting in exactly the same product as above, the conjugate base of my terminal alkyne, but the conjugate acid looks a little different. It's ammonia this time. The last one, CH3MgBr, it's a weird kind of compound, but it's carbon bonded to magnesium, bonded to bromine. It's essentially carbon with a lone pair and a minus. That is a little bit false, and we will spend a long time talking about compounds like these. Compounds like these are called Grignard reagents. Grignard reagents are a ton of stuff we will talk about next unit and next semester. So Grignard reagents, it's weird. We'll spend a lot of time on them. But for now, we're going to say this Grignard behaves like a carbon with a minus. That's a base. That base can take the hydrogen from my terminal alkyne, dumping electrons onto that carbon, leading to a carbon with a minus, the conjugate base of the terminal alkyne, and I create methane, CH4. That's my conjugate acid. Okay, can any old base deprotonate a terminal alkyne like this? Here's that acid-base chart that you're supposed to be familiar with, right? Yeah. Terminal alkynes are here. Terminal alkynes are reasonably acidic. It's the 5th most acidic thing on our list. Things that are less acidic than terminal alkynes have conjugate bases that can deprotonate a terminal alkyne. That means hydrogen. That means alkanes, alkenes, ammonia. The conjugate base of an alkane, the conjugate base of an alkene, the conjugate base of ammonia, the conjugate base of hydrogen. Those are the bases that can deprotonate a terminal alkyne. What I'm saying is, can hydroxide deprotonate a terminal alkyne? No, it is too weak. Equilibrium would favor reactants there. Oh, my Lanta. Remember, equilibrium favors formation of the weaker acid-base pair, always and forever. So there are only a few reagents that could deprotonate a terminal alkynes, and we saw 3 of them in the previous slide. There are not many. These 3 plus a little bit more, but you cannot use hydroxide even though you love hydroxide as a base. It's not strong enough to favor products at equilibrium. Once I have a terminal alkyne deprotonated, what the heck do I do with that terminal alkyne? Well, you do reactions like this, and you make yourself a carbon-carbon bond. Carbon-carbon bond forming reactions are the holy grail of organic chemistry. What does that mean? We really love reactions that make carbon-carbon bonds. I mean, we really love reactions that make carbon-carbon bonds, and this is the first one that we will talk about. This reaction takes the alkyne carbon that you have deprotonated, that is my nucleophile, and I attack the carbon that has a halogen on it, because the carbon with a halogen is partially positive. The carbon with the halogen is my electrophile. It's partially positive because the halogen is pulling electron density away from it. So what I get out of that is this brand spanking new carbon-carbon bond. That's a big deal to an organic chemist. I know it's not to you, but that's a big deal to an organic chemist. Making new carbon-carbon bonds tells us we can take small molecules and turn them into bigger molecules, and we get really proud of ourselves when we can do that. I was paused for a second to make sure that the words that are about to pop up are going to have room to pop up, and in doing that, I realized I said this is your first carbon-carbon bond forming reaction. That's not true. The Diels-Alder reaction makes carbon-carbon bonds. It actually makes two carbon-carbon bonds simultaneously. So there are two carbon-carbon bond forming reactions in this unit of material. I apologize for my misstep. This is a carbon-carbon bond forming reaction, so organic chemists love it. We get proud of ourselves when we can make big things out of little things. Okay. This type of reaction is a new kind of reaction. This is not an electrophilic addition reaction. All of those previous reactions, believe it or not, all of those previous reactions we've done are electrophilic additions. But this reaction is called an SN2 reaction. That S stands for substitution, that N stands for nucleophilic, and that 2 stands for bimolecular, SN2. We're going to talk a lot of details about types of SN2 reactions in the next unit, but let me give you a couple of details about it now, a little preview about it now, I guess. The SN2 reactions that we're going to see this unit are all an alkyne with a minus reacting with an alkyl halide. An alkyne with a minus reacting with an alkyl halide. The alkyl halide can be like the one given here. That's a methyl alkyl halide. They can be like this one. That's a primary alkyl halide. They can be like this one. That's a secondary alkyl halide. Tertiary alkyl halides cannot do an SN2 reaction, and that's good enough. That's all I'm going to say about the SN2 details right now. Let's go through a couple of synthesis problems. Are you ready? Let's do it. How would you synthesize 1-bromoethene? 1-bromoethene. Starting with acetylene. Acetylene is a common name, but unfortunately it's a common name. Yeah, I know that's silly to say. Acetylene is the simplest alkyne that exists. It's ethyne. Acetylene and ethyne are the same molecule, but acetylene is the common name of ethyne. Okay, so starting with acetylene, how would you prepare the following compounds? 1-bromoethane is what we're trying to synthesize. We're trying to synthesize 1-bromoethene from acetylene. Remember, this arrow means this comes from that. So if we were to present some forward synthesis details of how this works, we're going to take our acetylene and we're going to add, I need an H and I need a Br. But I really need to specify I'm adding one equivalent of HBr because I have an alkyne, I've got 2 pi bonds, one equivalent is mandatory. This is good. It's done. That's it. Starting with acetylene, how could you prepare 1-hexyne? That's 4 carbon, 5, 6. 1-hexyne from acetylene. The forward synthesis details would start with acetylene. And first, you must pluck a hydrogen from the acetylene. And you have to make sure that you're choosing a base that's strong enough to pluck a hydrogen from acetylene. Make that thing negative, and then add an alkyl halide. You need to make this carbon-carbon bond, the carbon-carbon bond that's got a squiggle on it over there, you need to make that carbon-carbon bond. That means you need an alkyl halide that has 4 carbons on it, and the halogen needs to be on the 4th carbon in the line. So 4-carbon alkyl halide, halogen on the 4th carbon in a line. Done. 1 hexyne. This is it. How would you make 2-hexanone? We don't know naming of ketones yet, but that's a ketone. 2-hexanone. If I come back through my knowledge of ketones, we've talked about ketones coming from enols. The ketone could come from that enol, or the ketone could come from this enol. The purple enol or the red enol is what would tautomerize to make that ketone. Okay, so if I'm trying to make this thing from acetylene, hold on, let me back up. This purple enol would have come from this alkyne. I hate that bond angle right there. That alkyne reacting with something to make that. The red would come from, let's see if I can straighten out the bond angle. It's a little bit better. The red would have come from that alkyne. So this alkyne is in the middle between two things. This alkyne is on one end. Is there a difference? Is there a better choice? Is there a choice that gets us all the points and a choice that doesn't get us all the points? Well, the purple is better in my opinion. We will get better at synthesis as we do more examples. But the purple is better in my opinion, number one, because look, it's 1-hexyne, and I've actually already shown you how to make 1-hexyne. Yeah, could you do it with the red? Yes. You would have to start with acetylene, deprotonate one end, add a single carbon with an alkyl halide, then deprotonate the other end and add 3 carbons with an alkyl halide. I like the purple one better because I only need to deprotonate and do an SN2 reaction one time. So I'm going to flush the red at this point, say let's not do the red, let's do the purple. So the purple retrosynthetic analysis needs to continue to say it comes from acetylene. And then the forward synthesis details would say acetylene. We pluck a hydrogen off of acetylene, and we choose a base that will pluck a hydrogen off of acetylene. We need a 4-carbon alkyl halide to react with that acetylide. That's the IDE version. That's the anion version. We need a 4-carbon alkyl halide to react with that acetylide. That gets me 1-hexyne. Note, it's the same thing. Then I need to have an OH be added here, not there. OH needs to be added on the secondary carbon, not the primary carbon. That's Markovnikov addition. And acid and water does Markovnikov addition. But truly, an alkyne needs some mercury to make the whole magic happen. So that says H2SO4, H2O, and HgSO4. That leads to this enol and no reagent needed. That enol, oh, it's getting real squeezy. That enol would tautomerize on its own to make that ketone. Oh my, yeah. Synthesis problems require you to put several pieces together. That's 2-hexanone. I need some space for 3-hexene. Give me a moment. I decided to pull it on over to a new blank thing instead of erasing. All right, so we're trying to make 3-hexene, but we're trying to make cis-3-hexene. Where that ene is, that used to be an ine. So, okay, because I need to make this from acetylene, I need that ene to have used to have been an ine. All right. And then somehow I got to make that ine from acetylene. All right. That's my retrosynthetic analysis. The forward synthesis details. I need to pluck a hydrogen off of my terminal alkyne, and I need to make sure that I choose a base capable of doing that. I need to add and make one of the bonds of my alkyne to the single bonded thing. So on this side, I've got 2 carbons, and I need to have a leaving group. 2 carbons with a leaving group, I get one side connected. This has to be a stepwise happening where I connect one side, then I connect the other. So then I pluck the hydrogen off of this other terminal alkyne end, and I add another 2-carbon alkyl halide to get me my 3-hexyne. And then, finally, I get to cis-3-hexene through reaction of H2 with Lindlar's catalyst. No exception, that has to be the case, because Lindlar's catalyst does syn addition. Lindlar's catalyst stops at an alkene. If it were H2 and palladium, we would get an alkane out of that. If it were Na and NH3, that's the dissolving metal reduction, that would give you a trans 3-hexene. H2 and Lindlar's catalyst is the only choice to get a cis alkene. Whew, that was a lot. I'm real glad this is the last video, aren't you? Peace out, yo.